So far in this chapter, we've been working with functions and differentiating them, and all of the functions we've worked with have been explicit functions, meaning they are written in a way so that like y is by itself on one side, and it's set up so that if you just plug in your input, it spits out the output, kind of what we normally think of as a function. So when it's written in a form like that, for example, this function here, 5x squared minus 7, because y is by itself, x is the only variable on the other side, we say that y is written explicitly as a function of x. However, not all equations or relations can be written in explicit functions. And an equation that defines a relation between y and x but does not explicitly define y as a function of x, we call that an implicit function. So before we keep going, I'll just note that this section is really like an extension of the chain rule. We're going to see the chain rule in an implicit form. Using the chain rule is going to allow us to find the derivative. It's going to allow us to get expressions for dy, dx, even if we don't have the function written in an explicit form. So here are some implicit functions. Here we start with the equation 3x plus 2y equals 6. That's implicit because it's not set up to write y as a function of x. Now, as it turns out, we could write y as a function of x, and if we do that, it looks like minus 3 halves x plus 3. This equation, y squared plus x equals 3, that's implicit. It's not set up to have y written as a function of x. In fact, we can't really define y as a function of x properly, because when we try to solve for x, we get two different functions, right? Two possible different outputs. Here we have another one, y to the 5th plus xy squared plus 3x squared equals 5. Certainly that's not set up as to write y as an explicit function of x. And in fact, you'd have a really hard time solving for y explicitly. Sometimes we just don't have an algebraic avenue to even get an explicit form. And then finally, here's an implicit function, but it actually doesn't define any type of real valued function because there's no real numbers for x and y that will make this true. X squared plus y squared is always at least as big as 0 because we're squaring them, and then we add 4, so that left side would have to be at least as big as 4 for all real number values. We've already worked with some implicit functions or relations, right? Our whole first chapter, we were looking at curves in the plane, and we looked at circles and ellipses, and those are not things that where we write y explicitly as a function of x. But they are still all things for which we might want to find the slope of a tangent line, right? It still would make sense to be able to say, oh, what is the slope of the line that just sort of touches the curve right here? And so this is what we're going to do in this section, is learn how to do that and get some practice. So the idea behind implicit differentiation is just knowing what variable we are respecting. That is key here. And in this section, we are always respecting x. And we can always tell what variable we're respecting because if you look at like the notation dy, dx, the bottom variable tells you what you're respecting. So these are all derivatives with respect to x. So we're going to start with this example. Our equation is y squared plus 2x squared equals 5. When we're doing this and we are differentiating with respect to x, whenever we encounter a variable that is not x, we understand that that variable is maybe some function of x, right? Maybe we don't have an explicit form for it, but we think of it as some function of x. So when we approach this equation, what we're going to do is just differentiate both sides with respect to x. We're used to working with equations. We know we're allowed to say add 2 to both sides to an equation, or multiply both sides by 5, or take the ln of both sides. Well, you can also take the derivative of both sides of an equation. So when we do that, right here, our very first term, we're going to apply the general power formula, and we get 2y. Now the chain rule says multiply by the derivative of the stuff inside. The derivative of the stuff, in this case, that stuff is y. So we're going to multiply by that derivative times dy dx. Our next term, 2x squared, we'll take that derivative. We get 4x times, well, the derivative of x is just 1. Now normally, once, if we're differentiating and we encounter the variable that is the same as the one we're respecting, we just understand that there's no chain rule that we have to worry about. There's no implicit chain rule we have to worry about there. Here I've just decided to write the times 1 to kind of show it out, but a lot of the times we'll leave out that times 1. And then on the other side, the derivative of 5, well, 5 is a constant, so its derivative is 0 regardless of what variable we're respecting. So look at the result here. We have an equation. We've got an equation where dy dx is in it. We want to find dy dx. That's our goal. That's our charge in this problem. So now we'll use algebra to solve this equation for dy dx. I'm going to subtract 4x from both sides. So now we have 2y dy dx is equal to negative 4x. And to solve for dy dx, we just need to divide both sides by 2y. So dy dx is negative 4x over 2y. We could actually reduce, I guess. 2 goes into 4 twice. So negative 2x over y. There's dy dx. Now, this, I'm going to just do a really rough sketch. Certainly we could use tools and get a better sketch, but if you're looking at this equation, if we think back to chapter 1, this is an ellipse, right? Both variables are squared, but they have different coefficients. It's an ellipse, as it turns out, that's oriented vertically. So something like that, and the center is at the origin. So even though we can't get y written explicitly as a function of x, it still makes sense that we might want to find dy dx. If you pick any point, its tangent slope is well defined, right? I might want to find a tangent slope. Also note that when we found dy dx, there was still an x and a y. It wasn't just a function of x. Now this happens a lot with implicit differentiation. We couldn't get y written explicitly just as a function of x, so it doesn't surprise us that dy dx we need to have both x's and y's in there. Also, when we look at this graph, of course we need to know both x and y if we're going to find the tangent slope. Like, what if I wanted to know, well, what's the tangent slope, right here at some value a? Well, when x is a, there's actually 2 different points I could be talking about. So this says, you actually need to specify both coordinates in order to figure out what the tangent slope is. All right, let's try another. We have to be careful with our algebra. I would say one of the hardest parts to implicit differentiation is dealing with some of the algebra that we have to do to solve. It isn't like tricky algebra, but it can get away from us sometimes. So we're going to differentiate both sides with respect to x. I know with respect to x because they want us to find dy dx. Also, we should just be careful here and note right off the bat, this right here, that's a product. X times y squared. I've got 2 variables multiplied. That's a product rule. So before I kind of start to doing the differentiation, I'm going to do a little side work for this product rule. So the first factor is f, so f is equal to x, and f prime is equal to 1. Our g factor is y squared. G is y squared. So g prime, that is 2y, but we're respecting x, 2y dy dx. All right, now let's start. We're going to just take the derivative of this equation term by term. Our first term, when we take that derivative using the power rule, we get 12y cubed. Now, we're respecting x, so we need times dy dx. Plus, here's where I'm going to have the product rule. So, g times f prime is y squared times 1. F times g prime is x times 2y dy dx. So this is that product rule. Next term, 2x cubed, that has a derivative of 6x squared. 6 is a constant, so that goes to 0. On the other side, 0 is a constant, so that goes to 0. So we have differentiated both sides. The first thing I'm going to do right now, I'm going to just clean this up a little bit before I start doing algebra. Okay. Now we want to solve for dy dx. Note that we have dy dx appearing in a couple of terms. So any term without a dy dx, I'm going to throw on the other side. I'll subtract y squared and subtract 6x squared from both sides. Now on the left side, keep our eye on the ball. We want to solve for dy dx. On the left side, both of our terms have a dy dx. We're going to factor it out. When we factor it out, inside now we've got 12y cubed plus 2xy. And now to solve for dy dx, we need only divide both sides by 12y cubed plus 2xy. So we get dy dx equals minus y squared minus 6x squared over 12y cubed plus 2xy. You could leave it here, or if you want, if you look at the bottom, you could factor out a 2y. Either's fine. It doesn't, it's not like we can reduce the fraction or anything. Okay, let's try another one. Maybe take a few seconds and size up this function, see if you can't spot, how we might map out how we're going to do this. When I look at this, right away I could see we've got a product right in the first term. So let's do some side work to set that up. Our f function will be 2x cubed, and f prime will be 6x squared. Our g function is y. Our g prime function, using the power rule, we just get 1, then times dy dx. So the derivative of y is, unsurprisingly, dy dx. So let's begin. Let's find this, let's differentiate this equation. Starting with the first term, we've got that product rule. So this will be g times f prime. So that's y times 6x squared plus f times g prime, 2x cubed times dy dx. So there's the first term. Now let's turn our attention to the second term. That's parentheses to a power. So we're going to apply that general power rule. We're going to bring this 3 down, right, and reduce the power by 1. So let's see, inside we still have y squared plus x squared, and then we're going to multiply this by the derivative of what's inside. So the derivative of y squared plus x, we'll just do it term by term. The derivative of y squared is 2y dy dx plus the derivative of x is 1. Now that finishes the left side of the equation for us. So then on the right side, the derivative of x to the 4th, that's a nice simpler derivative to take, just a power rule, so 4x cubed. All right, we want to solve for dy dx. One thing that makes this one a little bit harder than the last is that we have a dy dx inside a set of parentheses here, and we need to get it out. And the way that we get something outside of a set of parentheses is we distribute. Usually that's our avenue. So we're going to distribute this whole big factor outside, that 3 times parentheses squared. We're going to distribute that through those parentheses. Let's see, down here, I'm just going to clean this up a little bit. 6x squared y plus 2x cubed dy dx plus. Okay, now when we this factor that I'm putting in the red box here, when I distribute it to the 2y dy dx, we're going to get 6y times the parentheses y squared plus x squared times dy dx. And when we distribute it to the factor of 1, we'll just get that same factor that's in the red box there. So 3 parentheses y squared plus x squared. Okay. All right. Now, again, just keeping our eye on the ball, we want to solve for dy dx. We have our dy dx in a couple of terms. So any term without a dy dx, I'm going to subtract, throw on the other side. Alright, now on the left side, what we have is 2x cubed dy dx plus 6y times y squared plus x squared dy dx. On the other side, we got 4x cubed minus 6x squared y minus 3 times the square of y squared plus x. On the left side, all of our terms have a dy dx, right? Both terms have a factor of dy dx. Let's factor it out. So inside the parentheses now, we've got 2x cubed plus 6y times y squared plus x squared. And now it's all over but the shouting. To solve for dy dx, we're just going to divide by the stuff in the parentheses here. There we have it. All right, let's do another one. Our last example here, we're going to find the slope of the line tangent to this curve, x cubed plus y cubed minus 9xy equals 0 at the point 2, 4. So this is what the curve looks like there. It's sketched in blue, and they've graphed the tangent line for us. And we want the slope of the line tangent at the point 2, 4. So we want dy dx evaluated at this point. And before we even start, we'll just, looking at the graph, it looks like in that tangent line, we're going to expect to get a positive, right? That slope is definitely positive. It's not terribly steep, so a positive number that isn't particularly large. So let's begin. X cubed plus y cubed minus 9xy equals 0. Just taking a look at this equation, we can see, there's definitely a product rule here, right? That's a product. Now you got to be careful. I'm going to treat the product as 9x times y, and then I'm going to subtract what I get. You can treat the product as a negative 9x times y if you want, and then just add the result. That's fine too. I'm going to do some of this on the side. So our f function is 9x, which means that f prime is 9. Our g function is y, and so g prime is dy dx. All right, let's begin. Let's start differentiating. So the derivative of x cubed is 3x squared. And the derivative of y cubed is 3y squared dy dx. Now, I'm using brackets or parentheses, some sort of grouping symbols, because I'm going to have to subtract the whole product rule here. G times f prime is y times 9, or 9y, plus f times g prime is 9x dy dx. And that's equal to 0. So 3x squared plus 3y squared dy dx minus 9y minus 9x dy dx equals 0. Just taking a look here, often I would start by throwing anything without the dy dx on the other side, but what I'm going to do first is just divide everything by 3. Because there's a factor of 3 in every term. And of course that means I'm also dividing. I can only do that if I also divide the right side by 3. Of course that won't change what the right side looks like. Alright, now let's throw everything without a dy dx on the other side. We're going to subtract x squared and add 3y. And when we do that, on the left side, right, all of our terms have this factor of dy dx. I'm just going to go ahead, because we know it's coming. I'm going to go ahead and just factor it out now. So I got dy dx times y squared minus 3x on the left side. On the right side we got 3y minus x squared. And now we need only divide. So there's, this is the derivative. This is dy dx. This is what will give us the slope of a tangent line at any given point that's on the curve. So now we can finish. this problem, they asked us to find the tangent slope at the point 2, 4. So now we just have to make sure we plug in the right numbers to the right values, to the right variables. Y is 4 and x is 2, so that's 3 times 4 minus 2 squared over 4 squared minus 3 times 2. 12 minus 4 is 8 over 16 minus 6 is 10, 8/10 or 4/5. So a positive, right? We got a positive, and that wasn't terribly large. So that seems plausible, seems to jive with what the figure looks like in this problem up here.